My name is Chetan. So far we've seen a lot of the theory behind HTMs, how they work. Let's talk a little bit about what you can do today using HTMs. So I'll describe a little bit about what are the data and problem characteristics that are a good fit for HTM, and show you a couple of the applications that we've worked on that have those characteristics. Those are the applications that you could actually use today and start building on. Let's start with a little bit of review. So HTM, the HTM theory, of the theory we've so far implemented and commercially tested layer 2.3, which is the sensory inference sequence memory layer. So with this piece of HTM, we can do a lot of really cool things. I'll show you a couple of those things soon. And in progress, research in progress, we have the sensory motor inference layer. And this is basically the sensory inference layer in layer 2.3. What it is it's like a sensor looking into the world, and you have data coming out of the world. And it's modeling the temporal dynamics of that data. So it's learning the temporal sequence. The sensory motor inference layer, it's as if the model is actually able to behave in the world and learn a model of the world, not only due to the world changing, but also due to its own behavior. So layer 2.3, what we've implemented, we've already done a lot of really cool things and things you can use today. And the research for layer 4 will open up a whole new realm of applications, some really cool stuff that we can't even predict what kind of applications will come out of it. So with that in mind, let's switch gears a little bit and talk about data analytics. So data analytics today, how it's typically done is there'll be data being produced by the world. You have sensors into the world, and you typically take this data and you store it. You store it on drives or in the cloud. And at the end of the day, or at some period of time later, you go through and you visualize the data, or you build models on the data. This is what you typically see in big data processing, data analytics. The challenges with this approach, though, is that it requires people. So it's not automated in the sense that you need data scientists to go through and create models and create visualizations and understand the data. So it's a little manual. Models actually have a half-life because they're only mostly relevant at the moment that they're created, but as the patterns in the data change, the models become obsolete. And you have slow reaction times because you're storing the data and later on doing something with it. You're not acting on the data at the moment that it's created. We believe the future of data analytics is going to be in streaming data. Take data at rest, like it is today, and turn it into streaming data. So what this looks like is you have data streams. You may have many, many data streams. And you have online models. These models are in real time processing the data and creating predictions and actions as the data comes through. Some of the requirements for this kind of a vision are that you need automated model creation. So if you have many billions of these data streams, billions of models, you can't do it by hand. You need these models to be created automatically. These models have to learn in an unsupervised fashion because most of the data that's going to become more and more relevant is going to be unlabeled. It's going to be generated in real time. And because the patterns in the data are changing, we need these models to be continuously learning. We can't go in and hand tweak them when the data changes. We need them to automatically and in real time change and update and learn. So HTMs are a really good fit for the future of data analytics, which is streaming data. And I'll show you, let's go through a couple of the data and problem characteristics that have the future of data analytics, the streaming data, some of these data and problem characteristics. I'll outline here, and I'll show you how if you have these data and problem characteristics in your data, then HTMs are going to be a good fit to solve those problems. The first one, the most fundamental one, is your data time series. So what that means is, does the data depend on time? Is it change over time? And does it only really make sense as a sequence? So for example, a melody is a time series data because you're listening to each note as it comes in. and it only makes sense in order. Whereas a picture, there's no sense of time with pictures, so a picture would not be time series data. On the other hand, a series of pictures, like a movie, would be time series data. Now, a rule of thumb to decide whether your data is time series or not is, if you randomly shuffled the data, would that destroy it? Would it make sense? Would it lose its meaning if you looked at it out of order? If it would, then it's time series. Next question you can ask about your data is it high velocity? In other words, is it changing on the rate of seconds to minutes rather than on the rate of weeks to months? Because if your data is changing really slowly, or you're not sampling it regularly, then it's going to take a lot more time to learn the patterns in the data. They're not going to be as obvious. Whereas if it's high velocity, the models can quickly learn the patterns in the data. Next question is, do you need real-time predictions on anomalies? So HTMs are really good for this kind of a question because HTMs are constantly making predictions. So if you need real-time predictions and you want to take action in real time, which is, again, what streaming data is all about, then HTMs would be a good fit. Do you have too many individual data sources to handcraft models? So if you had a lot of data sources, it would be very expensive to go through and build a separate model for each one, tuned for the kind of patterns in the data sources. So if HTMs, you can do automated model creation. You can create a model that's general and works for any kind of a data stream and learns on its own. That's very useful because it frees you up to model a lot of independent streams of data. And do you need your models to learn continuously? So if the patterns in your data are changing, the model has to change with it. And it has to do this automatically. And finally, is your data unlabeled? If your data is unlabeled, then it's typically HTMs would be a good fit because HTMs can learn from unlabeled data. They can learn the patterns in the data without having to be supervised. So let's go over a couple examples of applications that have these characteristics. These are applications that you can actually use today. So because all these applications have those characteristics, they can be fit into this kind of a flow that we've seen this diagram. But it's basically the flow involves a metric or a set of metrics coming in. And we have a method by which we encode those metrics into SDRs, sparse distributed representations. Now, once you have an SDR, you can feed that into HTML learning algorithms, and it will learn the patterns in the sequence of SDRs, and it will create predictions and anomalies for you. So if your data has these characteristics and you can encode it, then you can feed it into HTML. So here's the set of examples of applications. And I'm going to be covering specifically these three. Let's go into a little bit more depth into these three. But note that all of these applications have all of those characteristics that we previously talked about. So let's go with the first one, server monitoring using Grok. In this case, what we have is we have a server or a server farm, and it's generating a bunch of metrics. So a metric coming from a server might look like CPU utilization or network usage. These are typically numerical. This is a number, like percentage of CPU usage. And what we do in this case is we usually sample this number every 5 minutes in the case of Grok. So this is a high velocity data stream sampled regularly. And it's a time series data because we're sampling it over time. And we take this and we feed it into a scalar encoder, which is what's available already. It takes a number and it creates an SDR out of it. And this SDR, when we feed it into HTM, HTM is going to be able to create anomalies, and whenever there's an anomaly, automatically create a notification. And in that way, you can take real-time action the moment that something unusual happens in your server. And typically, we're going to have many of these metrics, maybe many metrics per server or many servers. And what works well is we feed each metric into a separate model and have the model model that metric. And because HTM is automatically, the models are automatically created and they're continuously learning, all of these are, it can model all these independent metrics without much intervention from programmers. So with this kind of a system, we can detect some interesting anomalies in servers. We've seen a couple of those already. And it's easy to start using Grok with your own data on AWS. You can either use it with IT data that you collect through CloudWatch, or you can feed in custom metrics. And these custom metrics that you feed in, they don't have to be server data. It could be any kind of data that has the properties that we've talked about. This is the easiest way to get started with HTM, is feed your data into Grok, have it automatically create models for you, and generate predictions and anomalies and notifications. Let's look at the next application. Here's a totally different domain. Very different from servers. We have geospatial tracking. So you have a person moving around in the world and a GPS sensor, and we're trying to understand their patterns of movement. Now, even though it's a very different domain, I'll show you that it has all those characteristics, data characteristics, which allow us to use HTM to solve this problem. So in the geospatial tracking case, what we have is a GPS sensor that we're sampling every minute. So again, high velocity, regularly sampled, and we're reading the latitude, longitude, and speed off of this sensor. Now, we take this data and we feed it into a geospatial encoder. It's a special encoder that we have to convert geospatial data into SDRs. And that is available. You can actually find out more about how it works. You can go and read the white paper on our website for geospatial tracking, and the code is available as well. But it's pretty neat, and it creates an SDR out of this latitude, longitude, and speed data. Now that we have SDRs, we can feed it into HTM just like before, get anomalies and notifications when something is unusual happening with the person who's moving around. And again, we can do this for many independent models, many different people moving around. It doesn't have to be people. It could be trucks or anything that you're tracking in space. And all of these models are learning continuously and automatically created. So with this kind of a system, we can learn someone's route. So in this case, we had someone from the office drive home from work over a course of several days, and fed this through the HTM learning algorithms. And the first day, you see that everything is red, and red is anomalous because it hasn't learned anything yet. It hasn't learned any of the patterns yet. So the first day, everything's anomalous, and as you repeat this, as the person drove home from work, the second day it was less anomalous because it learned the general patterns in the data. But interestingly enough, that each point that was sampled, it was very different because of traffic conditions and because of noise and sampling at different points. So it's not learning, it's learning the general sequence, the general temporal patterns in the data, and it's understanding that. So the third day, everything is predicted, everything's nice and green, and it's starting to detect anomalies, true anomalies. So for instance, here's some of the types of anomalies that it can detect. It detected a position anomaly when the person drove off the road and back onto the road. That was unusual. Speed anomalies, so normally they're walking around, normally they walk a route, and one day they get into a car and drive to their destination. That was unusual because remember, we're feeding in the speed into them as part of the metric that we're encoding. And so when the speed changes, that's anomalous. And even when the direction changes, if the person, what the person did was U-turn on the road and come back and U-turn again, go forward, even though that exact, all the readings have been seen before, the actual sequence of SDRs that the model saw was different. And because it's a temporal data stream, it's a time series data, it was able to detect the anomaly in the sequence of events. So let's come to the third and last application that I'll talk about today, natural language. Yet again, a very different domain, but as you'll see, it'll have all the characteristics that we've talked about. And if we can encode it, then we could feed it into HTM. So for instance, here we have a temporal stream of words. So we have a text stream, and you can think of like a Twitter fire hose or something like that. And it's a temporal stream because the words make sense in order, and each new word that comes in, you can feed into the HTM. So with each word, you take the word, you feed it into a word encoder. If you have a word encoder, you can feed it in there and get an SDR. And again, you can do this for multiple streams simultaneously with separate models. Now, what is this word encoder? How do we convert a word into an SDR? That's a little trickier, but there's a company called Cortical.io that have done something pretty cool. They've created a system that can take a word and create an SDR out of it. And this SDR has all of the properties of a sparse distributed representation. So all of those bits, for instance, the SDR for the word apple that you get from their system, all of those bits that you can see active in the word apple, they all actually have some semantic meaning that is relevant to the word apple. So with just these SDRs, forgetting about HTM for a moment, we can do some pretty cool things with just these SDRs. For instance, you can take the SDR for apple and subtract out the SDR for the word fruit. What that means, what we're doing really is the bits that are active in apple, if they're also active in fruit, the corresponding bits, then we turn them off, right? So that's the subtraction of SDRs. If you subtract out the fruit SDR from the apple SDR, you get a new SDR. And if you went and looked up what this SDR was, what word it was closest to, what word it most looks like, you'll find that it actually looks really similar to the SDR for computer. So apple minus fruit equals computer. And this is really remarkable, right? And if you looked at other words that are similar to this SDR, you'll see Macintosh, Microsoft, Mac, Linux operating system, because all of these words actually have semantic similarities to the SDR for computer. So these SDRs actually carry some semantic meaning. So now what if we were to feed these SDRs in sequence to HTM? Could it learn something? So what we did was we did a little experiment. We created a small training set of 3-word sentences. So the first word is an animal. The second word is either eats or likes. And the third is what the animal eats or likes. So this is try to see if it can learn anything from this sort of structured data set. But remember that, so when you feed in these words, remember that the HTM is just seeing, all it's seeing are SDRs. It doesn't know anything about words. In the same way it knew nothing about geospatial data, it's just seeing SDRs, but it's learning the transitions between these SDRs. So we did something interesting. After training on this training set, feeding these sequences, we asked it to do something interesting. We fed in fox, the SDR for fox, and then the SDR for eats, and asked it to predict what the next thing would be. So in this case, note that the word fox, it didn't actually appear in the training set. The word fox never showed up in the training set, but we just asked it to make a prediction here. But notice that the SDR for fox is actually very similar. So it has some semantic similarity to other SDRs that it has seen in the training set, right? So it's similar, for instance, to the SDR for coyote, more so than the SDR for elephant, if you were to look at those SDRs. So if we fed this in, we asked to make a prediction, and it predicted an SDR that looks a lot like rodent. So it's pretty interesting to see that even though it's never seen the word fox before, it's able to make a semantic generalization at the lexical level of SDRs. Since it's never seen fox before, it still can predict based on having seen other SDRs that are similar. And at the grammatic level, it's able to know that the third word should be something like the third words in the sentences it has seen before. So note, this is completely unsupervised. We didn't actually tell it what words. It's just sequences of SDRs, and yet it's able to do this. And so this is a really cool demonstration of the power of the technology, the power of SDRs, and the power of learning sequences and HTM. And there's a lot of really cool applications in natural language using this kind of technology. So let's come back to this, your data. If you have, we have this system. We can feed in metrics, encode it, get SDRs, feed it through HTM, and get anomalies. If your data has these properties that we've talked about, if it has all of these properties, Then you can use an encoder that either exists today. We have a bunch of encoders that are there that you can use. There's a scalar encoder for converting numbers, date time encoder for converting timestamps, category encoder for encoding arbitrary categories. There's a geospatial encoder, and the word encoder by Cortical I/O. So you can convert your data into SDRs, and if your data is of a different type than these ones that I mentioned here, you can always create a new encoder, and we expect there will be many new encoders created over time. And if you have an encoder, you can convert it into an SDR and get predictions and anomalies to be able to make early and informed actions with your data. So there's a lot of really cool applications that are available, and really cool applications I'm sure will come out over time by people like you. That there's just so much opportunity, and there's a lot of really cool things that we can do. Thank you.
Questions? We have one here.
Oh, thank you. So, as I understood from you, I mean, if you have multivariate time series, like you are measuring multiple sensors, you do the learning for each one separately? How is it done? I mean, because usually you want to understand the context of an anomaly in terms of all the variables, like looking at one variable only may not give you the good picture of what's happening,
Yeah.
So that's what my first question. My second question, briefly, I mean, so far we haven't seen anything what is happening inside the learning, so it's kind of a black box for us. So what's the learning algorithm? What's the objective function optimized? And so on. I mean, this kind of stuff will give us more insight.
Okay, sure. So to address your first question, if you have multivariate data, so the reason I've shown a lot of cases where you have a model for a single metric or a single dimension is because typically in time series data, there's a lot of information in the temporal context. So usually, a certain metric, you can predict what's going to happen in the future based on the past data for that metric. If you have a lot of dimensions to your data, there's a couple options. We've found it works well to feed each one to a separate model and have the model learn from the temporal context. You can also use what we call swarming, where or it's particle swarm optimization. So it looks over all combinations of your metrics and tries to figure out which combination has the most information, is best suited to predict the quantity that you care about. So you can try to reduce the dimensionality and feed a smaller set to a model. So you can do that as well. And typically you just have to play with your data and see what works best. But HTM, one model, in our case, one layer, works best for a small set of metrics, a small set of dimensions on the order of 1 to 10, maybe 1 to 5. And you'll want to pick out the best ones to feed into the model. Your second question about the learning algorithms, we haven't not yet talked about it, but there's a lot of information up from the level of like documentation and talks that you can find out all the way down to the code. You can go and read the code, contribute to it if you'd like. It's definitely not a black box, very much the opposite. All of that information is on our website and at numenta.org. All the code is there as well. That's not in the scope of this talk that I've been given, but it's definitely, all that information is available to you.
Okay.
I think my data is already sparse. So I guess I can skip the SDR process. Is that right? Or do I have to ensure there are certain requirements on sparsity which I have to feed into the HTM algorithm?
So sparsity is one of the characteristics of an SDR. Also, you want the bits that are active in your data to actually have carry semantic meaning. Otherwise, it becomes hard to learn and generalize from the data. So that's what the encoders are there for. They're there to add in to convert the data into a sparse and distributed representation. So it really depends on what your data looks like. There are cases where if your data is really encoded in the appropriate format, looks like an SDR, then you can feed it directly into HTM. In the case of the cortical I/O word example, they actually produce SDRs for words. Their system acts like an encoder, so we can just feed those SDRs into HTM. But yeah, it would depend on what your data really looks like.
Thank you.
Thank you.
We're just going to take one more.
Yeah. This is a question on the cortical I/O example. So was the word fox never seen before, or was it seen but in a different context? In other words, why was the semantic meaning of fox similar to the semantic meaning of coyote?
Right, it's a good question. So it was never seen in the sequence training set that I showed that we used fed to the HTM. But in creating these SDRs, cortical I/O has taken the semantic meaning of these words and folded it into the SDRs that represent those words. So they have a process. I'll let them speak more to it, but they have a process by which they take a Wikipedia primarily, and they go through and they have a system by which they can create, they map words to SDRs, and these SDRs have those properties. And they have, I think you can find out more about talking to them about how their system does that. But the semantic meaning is encoded in the SDRs by the encoder, by the cortical I/O encoder.